The next idea we need to explore is the idea of the empirical formula. The empirical formula shows the ratio of the number of atoms that are present, not how many there are. So one of the most famous molecules you'll work with is the idea of glucose. And whenever you have the idea of glucose, you can say glucose is C6H12O6, and that's the correct formula. You looked at it in biology, you may have explored it a little bit in chemistry, but you see C6H12O6 a lot. That is the molecular formula. That is what is actually present in a molecule. Now, an empirical formula represents the lowest common, almost denominator of the number of elements that are present. So if you look, you can take all of these elements and you can divide them by 6. And when they all divide into 6, as far as a whole number ratio is concerned, you have what is called the empirical formula. It's like the reduced version of a molecular formula. So you come up with combustion analysis. Combustion analysis is the best way to see what a molecule is. And I know this doesn't make sense, but if you're trying to figure out what something is, what you can do is you can burn it in the presence of oxygen and you can see what that oxygen turns into. Specifically with organic molecules tend to be things that have carbons, hydrogens, nitrogens, and oxygens. Whenever you burn the thing and you see what comes out of it, you can measure what the resulting products are, and you can use that to go ahead and say this must have been that. Okay, so here's how this works. You generally have a trap that absorbs water, and you can measure this trap before and after, and whenever you measure it before and after, the mass difference represents the mass of water that's been produced. You can do the same thing with a carbon dioxide absorber. And so whenever you have the amount of carbon dioxide and water, you can therefore go ahead and say what the compound originally was. And here's how you do that. If you look at the data, you will be given something that looks like this. It will say the compound is 40.92% carbon, 4.58% oxygen, and 54.5% oxygen. So, if you were to look right here, how does that help us? The very first thing that you need to do is you would convert all the samples to 100 grams. So you would assume that instead of 40.92%, it's actually 40.92 grams. Instead of 4.58%, it's 4.58 grams, and so on and so on and so on. And then what you do is you convert it to the number of moles. So you see we take the idea of grams per mole, grams per mole, grams per mole, and now we have the number of moles of each one of the constituent particles. But you should realize that you can't have C 3.407, H 4.54. It doesn't work that way. You have to connect atoms in what are whole number ratios. So instead what we do is we say, all right, I'm going to take it and I'm going to divide it by the lowest one that there is. So the lowest one that we had was 3.406. And so when you take 3.407 and divide by 3.406, it is essentially 1. So we can say that there's 1 carbon. When you take 4.54 and divide by 3.406, you get 1.33. And if you look at oxygen, we originally had 3.406, so oxygen is also going to be 1. But still you have a problem. You can't do C1H1.3301. So instead what you have to do is you have to multiply it by the number that will give it a whole number ratio, and that's what you see here. You see the idea that C3H4O3. Now this is not necessarily the molecule, okay? It is not necessarily the molecule. It is the empirical formula, which means it's the lowest combination of these to actually get them to fit. It's the lowest common denominator. Now, that does not mean that it's not this. It could be C3H4O3, but it doesn't have to be. It could be C6H8O6, or any combination of those that you can multiply by a whole number. So we look at our first example. It says you have an unknown hydrocarbon that has the empirical formula of CXHYOZ, and it says determine X, Y, and Z using the combustion data. Okay, so the first thing that you've got to do here is you convert all of these things to grams. What you can do whenever you have something that looks like this is that it is an extremely small amount of oxygen. It is possible that you're going to have something very large like C 1000, H 1500, O1, but it is unlikely. Based on the experimental concept that we had here, where we're pumping excess oxygen through, and then you're measuring the oxygen that leaves, it is far more likely that instead of having this 0.011% oxygen be from the compound, it is more than likely a contaminant. And as far as how you know that, you have to start to get a feel for these things. But basically, it's less than 0.1%. So it's generally considered to be a trace at that point. Now, it could possibly be it, but we're going to go ahead and leave it off for now, and we're going to assume that it's just a trace element. So you convert this to grams, like we said, and then you divide by the molar mass. So 84.17 divided by 12.01, hydrogen would divide by 1.008, and that's the number of grams that you have in 1 mole for carbon and 1 mole for hydrogen. Okay, once you do that, you actually get the number of moles, and that what we have here is we've got 7.0039, and on the other side we have 15.746. Divide both sides by the smallest one, which is 7.0039, and what you end up with is you get 1 for carbon, and for hydrogen you get 2.25. You should realize that 2.25 isn't going to work, but if I were to multiply it by 4, I would get a whole number. So that would give me 9 for hydrogen. But what you do to one of them, you've got to do to the other, so we multiply that by 4, and you have carbon 4 and then H9. So that represents the empirical formula for this particular compound. It does not mean that it's the molecular formula.